Unit 1 is all about limits. Okay? A limit is the behavior of a function as x approaches some value. And we are going to spend 3 weeks looking at limits. Today we're going to start very basic. We're going to look at what happens numerically. It's not going to be the way you're really going to look at limits, but to start to get an understanding, that's what we're going to do. We are going to look at limits graphically today. So here's a graph. How do we understand what's happening? All right. And then tomorrow we'll start looking at limits algebraically. And that's really where a lot of our practice is going to come in, looking at the different strategies that we can evaluate limits if we have like an equation as opposed to a graph. Okay. Okay, so what's happening is x is approaching a value. We are concerned what the y values are approaching. Notice how I'm using the word approaching. I'm not using the word equals. I'm using the word approaching. So just look at this table right here. Okay, do you notice in our table that this, if we come from the right and the left, our x values are getting closer and closer to 1. All right? Look at the y values. If you were to take a guess, what does it look like our y values are approaching? Okay, so over here, our y values get bigger and bigger up until we think they're approaching 3. Over from the right side, they get smaller and smaller. It looks like they're approaching 3. Okay? So this is what's happening. We have an equation. Okay, I wouldn't write this down quite yet. What I would write down is this, so you can see the notation. So the limit as x approaches 1, that's how we read that. The limit as x, you're going to have an arrow. We say approaches 1. And then go ahead and write in x cubed minus 1 over x minus 1. Equals 3. Like this is what I would be writing down if I were you. What I wrote in blue. Okay. So LIM stands for limit. You're going to have an x with an arrow and a number. And it might not be x, but since our function is in terms of x, in this example it's an x. If our function is in terms of t, that would be a t arrow and number. Okay? But we read it, the limit as x approaches, in this case, 1. Our answer is 3. As x gets closer and closer to 1, our y values get closer and closer to 3. We are approaching 3. Now, look at the graph. And you may want to draw this so you have this picture in your notes. What's happening at x equals 1? Y equals 3. What's there? An open circle. We have a hole there. There's not even a function value there, but that's okay. Okay? When we think about a limit, we are looking at what the y behavior is from both sides. So if we're looking at a graph, I kind of like to imagine like, hey, I have kids. I have 2 small boys. We have lots of Hot Wheels at our house, right? If I were to take a Hot Wheel and I would drive it on the curve, what y value are we approaching? So if I were to put my car here, my y value is approaching 3. Over here, I drive my car. My y value is approaching 3. From both sides, the y value approaches 3 the closer we get to x equals 1. So our limit is 3. We're going to do this again, okay? And really, all day today, we're just getting our mind wrapped around the these pictures of what a limit looks like. What I want us to do first, and I want to be clear, this is not how we are going to evaluate limits after today. But I want you to get an understanding about what's happening numerically. Okay? So get out your graphing calculators. In order to help us understand the limit as x approaches 2 of this rational function, I want us to plug in some numbers and look at what's happening numerically. Okay? So there's 1, 2, 3, 4, 5 of this. 1, 2, 3, 4. So pod 1, I want you to plug in 1.75 and 1.9 and tell me what those y values are. Pod 3, I want you to do 1.99 and 1.999. Pod 3, that's you. Pod 4 and 5, I want you to plug in 2.001 and 2.01. And then pod 6, I want you to plug in 2.1 and 2.25. It's okay to talk to each other too. You're dividing all of that. If you're dividing, you want your numerator all in parentheses divided by your denominator all in parentheses. Don't forget about those orders of operations.
When you divide your answer, you have to divide all your calculator would take it by.
Okay. Pod 1. What did you get for 1.75? Do you have 1.9 yet? Okay. Pod 3. What do you have for 1.99? 1.999. Okay. Okay. 2.001. 2.01.
1.01.
2.1. And 2.25.
1.2.
Okay. Okay. So as our x values from both sides get closer and closer to 2, the limit as x approaches 2, what is happening to our y values? They are getting closer to 1. So we can say that the limit as x approaches 2 of x squared minus 3x plus 2 all over x minus 2 equals 1. Okay? Now, that is tedious. And if we have some sort of like fractional answer that we're approaching, not really accurate. Okay? If we're approaching an integer value, okay, this isn't so bad, but man, do you really want to plug in all those numbers? No. So that's really not a good way of doing it. Okay? However, it's a good way to kickstart our understanding of the idea. Now, let's think about what this graph looks like. Do you remember graphing rational expressions? Okay, well, the first thing that me or Miss Cronky asked you to do was to simplify in case there was anything that could cancel out, right? Can this simplify?
Yes.
Okay, well, what is this factor 2 in the numerator?
X minus 2.
Like that? Ooh. Okay. So what's happening? What do we have? We have a hole. Yep. So we have the line x minus 1 with a hole at x equals 2. Graphically, this is what's happening. So, we can take our Hot Wheels car. When we drive our Hot Wheels car from either side of x equals 2, our y values get closer and closer to where this hole is, which is at 1. If I ask you, what is f of 2? There is not an f of 2 because there's a hole. But the limit as x approaches 2 would be 1 because we are approaching where that hole is. We're getting closer and closer and closer to 1. Okay. Now, do you think that there are times where maybe a limit it wouldn't work? Okay, let's talk about those cases. Okay, do you have an idea, Max? You were really quick to say yes.
Well, like if there's no hole there, I don't know, because there's been one every time so far.
There's been one every time. Well, I will tell you that if this were just the line y equals x minus 2, our limit would still be 1 because we're still approaching 1, even if there's not a hole there. Okay, so that's a good point. It actually makes it easier because we can think about what the function value actually is. Okay. But what if, like you guys just graphed some, forgot I had this example. Sorry, guys. What I want you to do, so we're going to come back to when the limit doesn't exist. But what I want you to do is I want you to, at your pod, turn to each other. What's the limit as x approaches 2? The limit as x approaches 2 of this graph. Turn to your neighbor. What is it?
X is constant.
Yeah, well, I guess you just get right. So,
And it's
I don't-
the limit is
Because they have a point at 2.
If you drive your car.
Still, that's what doesn't make sense.
So it's just arbitrary
Yeah, I can pick any x that's in the domain to ask you for.
Well, it's good,
Yeah. And then you just go to that piece of the graph.
I was just wondering because
Since there's a hole,
approaches to
it's still holes on
So I'm picking 2 because that's where the hole is, so that there's something interesting there. But I really could ask you any x value. Okay, I've just been kind of picking the more interesting ones. Okay. What do you think, Alex?
You said 1.
You said 1. If we drive our car on the function, we would approach y equals 1. Now, if I ask you for f of 2, what would your answer be?
0.
F of 2 would be 0 because that's where the coordinate is. But the coordinate is not connected to the graph at all. Our limit is based on where the curve is. Okay? So where we would drive our car along the curve, that's what we're interested in for our limit. What's your question?
I don't know. This doesn't make any sense to me. Keep going. I'll figure it out.
Okay, so let's get a couple examples in, and then maybe you'll come up with how to express your question. Okay, so, and maybe talking about when it doesn't work will also help. So there are 3 scenarios in which a limit fails to exist. Okay, and when a limit fails to exist, we write DNE, does not exist. Okay, sometimes I get excited about those. DNE. to give you pictures for each one of these. Okay? So the first one. Our function is approaching a different number from the right than from the left. Write it down, I'll give you a picture. The function value approaches a different number from the right side than the left. If I make you pull out your quizzes, there is a graph on your quiz in which we could use as an example. Okay, so if we are approaching a different number on the right side than we are from the left side, then the limit does not exist.
Aha. Aha. I get the
Thank you. Who does not get it? Okay, what movie is this? Okay, good. Last year I had this up and everyone was like, I think Netflix has helped me out with this, at least. Okay, here is a picture. So we have, write down, like this is your picture, this is your example, the limit as x approaches 0 of absolute value of x over x. And then I want you to draw this picture, and this is a graph that I want you to remember. You've never seen it before, that's fine. But I need you to remember that this is the graph. We have a hole at 0, 1, and we go to the right. We have a hole at 0, -1. We go to the left. Okay. So if we are looking at the limit as x approaches 0, if we drive our car on the curve, I'll let you drive down first. I'm getting excited. So if we take our Hot Wheels car and we put it on this part, right, as we drive closer to x is 0, our y value approaches 1. But if we take our Hot Wheels car and we place it to the left of 0, the curve is down here, and we approach -1. So we're approaching 1 from the right, -1 from the left. They're not meeting up, which means the limit does not exist. So you would write D and E. Kind of, yes. Okay. So if there's a break in your graph, like those piecewise functions, if there's a break and I'm asking you to find the limit at that break, if they're not matching up, that limit cannot exist. Yes.
So then can there be like a limit not on the break?
So if I ask you for the limit as x approaches 1 from this graph,
Yes.
what would it be, Max?
1.
It would be 1, because here's x equals 1, so from the right and from the left, our y value is here at 1. Mm-hmm.
So if one of those were a closed circle, then there would be a limit?
No, because we are still approaching different y values from each side. Okay, if they met, that would be good, but they're separated. Other clarifications? Do you see how they're at different levels?
Yeah.
So since they're at different heights,
No, I get that.
okay,
I don't understand how you're doing the bottom.
like how I got the graph?
Yeah.
Okay, the graph you've never seen before. But I want you to look at this graph and remember that it goes with this equation right here.
Okay.
This is something new to you. So I want you to like put that in your toolbox. It's like if I gave you, it is possible like in your note or in your homework. Like if I gave you the limit as x approaches 5 of the absolute value of x minus 5 over x minus 5. That's very similar to what we just talked about, but it's a different function. It's the same graph, but what happened to it?
Shifted.
Shifted where?
Does that mean they're farther apart?
It just shifted to the right 5 because x minus 5 is inside of our function. Right? Okay? Just like if we had x minus 5, the quantity squared, we would have a parabola shifted to the right 5. Okay? So that's why I just need you to remember what this graph looks like. It's new to you, but you need to keep it in your memory. Okay? All right, case number 2, where our limit doesn't exist, is when our function increases or decreases without bound. Without bound, it goes on for. So if f of x increases or decreases without bound, then the limit does not exist. Here's what this looks like. This is the graph 1 over x squared. Man, it just got it's really big. Let me make it a little smaller. Not so big. Okay, so this is the graph 1 over x squared. And I'm asking for the limit as x approaches 0. Now, anywhere else, we could evaluate a limit based on where the coordinates are. But at 0, what's happening? We're going on. We're increasing without bound in this case. Essentially, there's an asymptote. And when we approach a vertical asymptote, we either go towards positive infinity or we go towards negative infinity. Okay, I know they're going in the same direction, and we'll talk about this case here in a couple days, next week, and how we can describe it. But officially, the limit does not exist because we are increasing without bound. Max, to kind of follow up on your question from before, like I could ask you for the limit as x approaches 1, and you could tell me 1. I could ask you for the limit as x approaches 2, and you could tell me 1/4. Okay.
So it's just because they don't connect. That's why.
Well, yeah, it's because they're going towards infinity. Like they're increasing, and it's never going to stop increasing. Okay. So anytime there's a vertical asymptote, we're going to have that behavior, and so that limit won't ever exist.
So is there a limit as well at the horizontal limit on this graph? Like if you ask, I don't know how you would ask for if y equals 0.
Well, it's always going to be as x approaches something. So I'm always going to ask you for your domain piece.
Okay.
So like I was talking to Max, I can ask you for the limit as x approaches 2. And here, as x approaches 2, our y value approaches 1/4. I could ask you that. But at 0, that's the only place where it's not going to exist because of the asymptote. Okay? All right, the last one is the craziest one of them all and the least likely to occur. And that's when f of x oscillates between two fixed values as x approaches c. And this graph is probably the most exciting to draw. So get ready for it.
What is C?
So I'm referencing c as like the x arrow going number down there, like as x approaches whatever number. I'm generalizing it as that c because it's going to change from problem to problem.
So it's just whatever you're going towards.
So just to be clear, this c that you're writing down, that's whatever x is approaching. It's going to change from problem to problem, so I generalized it as c, just some constant number. Okay? So if f of x oscillates between two fixed values as x approaches c, then the limit does not exist. And this would be an example, of that happening. Do you see how we oscillate between two fixed values as we approach c?
Yes.
Okay? Like I said, this is a very exciting one to draw in your notes because you get to go. I mean, it's scribbly. It's fine.
So like any sine, cosine.
Well, sine and cosine, like sine of x, cosine of x, are going to be okay because yes, they oscillate, but they oscillate at an even tempo to where we can tell what those values are. Can you tell, like if I were to point, could you tell where we would be? And so this is the case where it's oscillating, but like really quickly at an accelerated pace to where we can't tell what the heck is going on.
Let's just give it a
But, Brayden, you're right. It's going to occur in instances with our trig functions because the normal ones oscillate at a nice pace. Okay? So this graph is the sine of 1 over x. Really, everywhere else it's fine. But as we approach 0, that's where we get this oscillating behavior that's crazy. And we can't tell what's going on. So we have to say that the limit doesn't exist. Okay. Yes?
But we can still find the limit somewhere near that blurry max, like somewhere.
Yeah, if I asked you for the limit as x approaches 1, we'd be able to do that.
What about it's like 0.002?
That's probably still not okay because of all. Well, actually, it would be okay because tomorrow I'm going to teach you something called direct substitution. Okay, and so I will come back to that tomorrow. Okay. All right. So what I want you to do, really, we just need practice at this. We need to wrap our heads around what's going on, and everything we're going to do from here on out is going to involve a graph. So I'm going to go to my next slide. I'm going to give you about a minute to draw the graph down roughly. It does not have to be beautiful. This is just your notes. Okay? But if we're going to go through examples, it's going to be hard to do that if you don't have it written down. So take about a minute and draw down the best of your ability this graph.
I got a graph.
If you get those 3 holes down and the solid dot, and then just connect everything else, you should be okay. illegible. Okay. So what I'm going to do, I'm going to reveal like 4 or 5 questions that I want you to work together at your pod to answer. Okay? I'll give you about 2 minutes to do this. Okay? So 4 questions. I can remember how many. Work together to answer these questions.
Do you want to put this to like the whole number? Or
Just
like,
right.
That first one might not be an integer.
okay.
And so estimate to the best of your ability. Okay, that first question I realize might not be an integer, so estimate, that's okay.
That would be a DNA, I think. One with the solid though. 2.
Drive your race car.
Yeah, it's the race car fell off.
Oh, it's a DNA.
Where did it fall off?
Yeah.
That makes more sense. Yeah, so that's that question, like, what is it?
How are you getting
For what?
That was so confusing. I was like, sit down. I'm like, what's a limit? I have a definition.
The dot is.
Y is this 2, not from the solid point right there. So that one is in the middle, and then for the other ones, you're just watching it like come. So for the second one, since it's like split off, that's why it's the end function. Because car as it goes one, car
So then
falls
it's just gonna get.
Well, if it's as is approaching 1, wouldn't it be like 3.3 or something? Like you follow it coming onto it? On the end?
It's not even, but it's not getting to 1. It's
That's why you do bad colors.
Okay. Let's come together. Trenton, what do you have for the limit as x approaches 3? 1.5. Okay, I've seen some like 1.75, 1.8. We're kind of estimating there. That's fine. All right. But here is x is 3. As we approach x is 3, we're approaching this coordinate, which is there. Okay, which is 1.5, 1.75, whatever you estimated that to be. That's fine. Okay. Dylan, what about the limit as x approaches 1?
There is another.
Okay, and why is that?
Because they don't line up.
Okay, so if we come from the right side, we approach 1. From the left side, we're approaching like 3.5. Okay, those aren't the same. They don't match, so the limit does not exist. However, our function value, f of 1, Allie, what's that? You say that reluctantly, have some confidence. We have a coordinate right here. When x is 1, our coordinate is at y is 2, so that's our function value. That's exactly right. Okay? And then Kinley, what about the limit as x approaches 4?
We put 2.
Okay? At x is 4, there's a hole right there. But as we approach from the right and left, our y value is approaching that hole, which occurs at y equals 2. Okay. Questions? As a time saver, don't write this down, but instead just talk about at your pod for 60 seconds. What x values does the limit not exist at? 60 seconds. Go. Yeah.
And then what about the one? That like not quite negative one going that negative 2.
All right, eyes up here. Xander, give me one, please. 0. And what's the problem at 0? Okay, so at x equals 0, our right and left hand limit do not match. The limit does not exist. Okay? Ethan, give me another place.
4.
X equals 4. What's the issue there?
They are going first.
Okay, we're increasing or decreasing without bound. Owen, give me another one.
Negative 2.
And what's the problem there? There's an asymptote. So we're increasing and decreasing without bound. Or you could say that they don't match up. Either one. Okay, hey, I still have a minute and a half with you. Cool your jets. Okay. Does the limit exist at x equals 2?
Yeah.
Okay, Max, what is it?
Huh? It's like half.
It would be like 1/2. Okay, as we approach x equals 2, our y values approach the hole, which is at a height of 1/2. Okay, all right, my hopes was to do an activity to get you out of your seats, but we'll just start with class. We'll start that with class tomorrow, okay? So, like, I'm going to give you a problem, and you're going to have to decide the answer and go from there. So, your homework. Bolded problems, you have 1, 2, 3, 13 problems. And if most of them are graphs, I'm going to take it off. Okay? Tomorrow, I will check your homework first thing. So have it out on your desk, ready to go. Okay?